All right, well, good morning. Today we are going to do chapter 2. Before we do chapter 2, we will do the last section of chapter 1. But before we do any of that, the Academic Success Center asked me to put this up, just in case anybody's interested in tutoring. I've never been there, so I don't know, but they're apparently in A100. They are available face-to-face and virtually through Microsoft Teams, which I think is Microsoft's ripoff of Zoom. Here's their email. You can call and see and whatever, but these are the times that they have tutors available for 110. Any questions? Before we do the last of chapter 1, let me show you one last thing on Blackboard. And it's the link here, review videos. Now, like I said, the entire lecture here is recorded. But it's typically an hour, 45 minutes, 2 hours long. It's up on YouTube. So it's easy to scan and find something if you have a question. But these guys make it much easier if you have a specific question. For example, when you click on the thing, this is what you see. These are all 10, maybe less than 10, maybe 5 to 7 minutes long. And they're videos about a single topic. So if you didn't quite get what I said about significant figures, you can click on the link here, and you get something like this. Again, this is, 7 minutes. So this specifically addresses everything we talked about in significant figures. And there's a whole bunch of these, 35 or 40, all throughout the semester. So it makes it easy. You don't have to go and find something. Any questions? All right, this is the tail end of chapter 1. We're going to talk about electron configuration, orbitals, and just a tiny bit about the quantum mechanics leading up to it all. I'll be honest, this is general chemistry material, okay? Most people won't teach this in intro, but I like to because it helps with the concept of valence electrons. In chapter 3, we're going to deal with bonding, which means you need to understand the highest energy electrons in a given atom. Those are the valence electrons. This will give you a very simple overview of electrons around the atom and which we consider to be valence. So that's why we're doing it. It's just a quick overview. In general chemistry, you would do this in great detail. All right, when we talked about carbon, we said that carbon has an atomic number of 6, so neutral carbon has 6 protons and 6 electrons. The image that I put up was something like this, little tiny nucleus in the middle, and these represent the electrons around it. At the time I said, you'll note that these electrons are in 2 energy levels. The reason for that is that carbon is in the second period. And we'll see that the period dictates the number of electrons or the number of energy levels in a given atom. These guys that are in the middle, These are called the core electrons. They really aren't involved in bonding or anything like that. They're just there. They're negative, they neutralize the charge on the nucleus. But these guys on the outside, these are the highest energy electrons. These are what we will call the valence electrons. These we want to know about because this is how we make bonds. Now, as I said, the number of energy levels or quantum levels in a given atom is dictated by the period in the periodic table. Again, carbon here in the second period has 2 quantum levels. Each quantum level can hold a certain number of electrons, 2n squared, where n is the period number. So we do 2, 8, 18, 32, 50, etc., etc. We are only going to deal with the first 3 periods here, okay? You can save the rest for general chemistry. But, so 2, 8, and 18 are what we're looking at. Within each of these energy levels, electrons live in something we call orbitals. Now the simplest, lowest energy orbital is called an S. We also have P, D, and F. Each orbital can only hold 2 electrons. An orbital is nothing more than a calculated region of space where you are likely to find the electron. For the S orbital, it's a sphere. Other orbitals get much more interesting. When we have more than 2 electrons in an atom, we start putting them in the second period, and they go in p orbitals. Now, remember, each of these can only hold 2 electrons. Now, it's really tempting to look at something like this and say, okay, I got it. 1 electron here, 1 electron here. Doesn't work that way. Quantum mechanics tells us that somewhere within these loads, we have 2 electrons. We have no idea where they are, but there are 2. One thing we know, however, is that they are never, ever in the middle. Somehow they go from here to here without ever being in the middle. It's the magic of quantum mechanics. So we have 3 p electrons, or p orbitals, and each can hold 2 electrons. The D's come next. D and F orbitals are very interesting geometries. My favorite here is this guy. It's a lobe with a little inner tube around the middle. And once again, quantum mechanics tells us that somewhere within this region of space, all of it, except the middle, we have 2 electrons. F orbitals are even cuter. Here's one with 2 inner tubes, etc. Any questions? All right, let's start with our first 3 periods, and we'll do period 1. Period 1, we can hold 2 electrons. We will put 1 electron here for hydrogen. The second electron goes here and makes helium. Both of these go in the lowest energy orbital, and that will be the s orbital. We refer to this as the 1s. Once we have 2 electrons in the 1s orbital, it's full. So we move to the second period. The first 2 electrons go here. Lithium, beryllium. These go in the lowest energy orbital first, that's the s. So we have 2 electrons in the 2s orbital. Once it's full, we move over here and we do the p orbitals. we have a total of 1, 2, 3, 4, 5, 6 electrons we can deal with. Each p orbital holds 2, and it looks like this. For something like carbon, we put 1 electron in first, and then we put the second electron in second. The third period, first 2 electrons again, go into 3s. Now, you would expect the next thing that would happen would be that we would fill the 3d. It's there, but we don't. Some work of nature says we will not fill the 3d yet. Instead, we'll put the next electrons into 3p's. So we put 2 electrons, 2 electrons, and 2 electrons. Our third period is now full. What happened to the 4 3ds? Well, again, it just turns out that if you do the energies, the energy of the 3ds is slightly higher than the 4s. So we don't fill the 3ds yet. Instead, we fill the 4s first. Then these elements in here go in the d orbitals. These are 3d orbitals. Once we do that, we go over here and we fill the 4p's. Now, like I said, we're only going to deal with the first 3 periods. Makes it really simple. If we look at our periodic table in terms of how it fills and why it looks this way, we have 2 electrons can go in the 1s, 1, 2, and then 6 more in the second energy level, 2s and 2p's. 3s, 3p's, and then we start the other stuff. Again, this is the focus in this course. Any questions? All right. Let's go ahead and do an electron configuration. Let's start here with our old friend carbon. Again, atomic number of 6, neutral carbon, 6 electrons. 2 of these are going to be at our first quantum level. N is 1. The other 4 are going to be in the second quantum level. What we're doing is we're filling this with the first 2 electrons. The next 2, we fill this guy. Here's carbon. So the next 2 electrons go here and here. The 1s electron, or 1s orbital, is full. We show that with the shorthand. 1 for the period, s for the orbital, 2 superscript, or the number of electrons. 1s2. The 2s orbital is also full. 2s2. Our p orbital has 2 electrons, 2p2. If I asked you to write the full electron configuration, you would write 1s2, 2s2, 2p2, and it would look like that. Now, of these electrons, these guys in the first period are the core electrons. We don't care about those. These 4 that are in the second period, they're the highest energy, and those are valence. We will use those 4 electrons to make bonds. Any questions? Well, there is another ringer Okay, quantum mechanics does this. It assigns properties to particles. So there are 4 properties assigned to an electron. One of those is the property of spin. Now, electrons are not little balls, and they really don't spin. But quantum mechanics says there's a property that relates to that. Since the electron is charged and it's spinning, it generates a magnetic field. The magnetic field can either be oriented this way or this way. We show that with little arrows up and down. Okay, so within any orbital, we're going to have 2 electrons, and something called Hund's rule tells us that one is going to be up and one is going to be down. If we were looking at p orbitals here, Hund's rule tells us the first thing we do is put in 1 electron at a time until all the orbitals have 1. Then we start to pair them up with the opposite spin. So up, up, up. A 4th one goes in, down, and then down and down. Now, again, this is getting a little bit past just the concept of valence. But, to be honest, the tutorial on this was written for a general chemistry class. And so you kind of need just a simple understanding of Hund's rule in order to do it. But that's as far as we're going to go. Let's do another configuration. Oh, let's show this configuration with arrows. For hydrogen, 1s orbital, right there, 1 electron. It's going to go in, and it's going to be up. We get over to helium, we have 2 electrons, also in the 1s orbital. One is going to be up, and one is down. 1s2, 1s1 and 1s2. Any questions? All right, let's just do a simple thing for fluorine. Fluorine, atomic number of 9. Neutral fluorine has 9 electrons. 2 are going to be in the first, 7 in the second. It will have 7 valence electrons because those are the highest energy. Here's our configuration. Fluorine is over here, second period in group number 7. Okay, that means that the 1s is full. 1 up, 1 down. The 2s is also full. 1 up, 1 down. The 2p, we have 3 orbitals. We will put them in 1 at a time, up, up, up. Now we have a total of 5 electrons here, so we put it in down and down. The complete configuration looks like this if you use little arrows. And if you write the abbreviated, this is what you would do. On exams, we will do this. Okay? But make sure you understand this for the tutorial. Speaking of exams, let's look at a problem or two. electron configuration for sulfur is what? First thing you need is a periodic table. Here's one. Second thing you need to do is to find sulfur. There it is. All right. Sulfur is in our third period, and it's in group 6. That means that the first energy level is 4. We write that simply as 1s2. Second energy level, we have 2 electrons in the s, and we have 1, 2, 3, 4, 5, 6 in the p orbital. Third energy level, first 2 electrons go in the 3s. And now over here, we have 1, 2, 3, 4 electrons. We write this as 3p4. 1s, so let's see, what is it? Here, 1s2, 2s2, 2p6, 3s2, 3p4, yep, that's the right answer. The valence electrons for sulfur are the highest energy, and they're the ones here in the third period. 1, 2, 3, 4, 5, 6 valence electrons. Any questions? Let's do another. This was put on a test as a trick question, sort of. Sorry. Here's lithium, here's some numbers, they don't matter. Number of electrons in the highest energy shell is what? Well, lithium is here in the first group, second period. It has a total of 1, 2, 3 electrons, doesn't it? But the highest energy electrons are the valence electrons, aren't they? These 2 are the core electrons. It has 1 electron in the highest energy shell. Any questions on these?
Can you explain this question?
Sure. Explain what?
Why is it 1?
Has 1 electron. Here's the configuration. 1s2, so these 2 are filled, right? Here in the second period, we only have 3 electrons to work with, so we put them 1, 2, 3. Highest energy, highest period number, 1 electron. Makes sense to me.
You've been teaching us for years.
I have, actually. All right, here's the tutorial. And again, the tutorial that is designed for practice on Chemistry Online requires you to understand the concept of Hund's rule. The quiz that's on Blackboard does not. Remember, you get points for the quiz, but it's a nice practice anyway. And it's always nice to understand Hund's rule. We're going to go back to sulfur again. We just did sulfur, right? Here's our periodic table, and here's sulfur. On this tutorial, you have a whole bunch of little blocks. And you must either enter a 1, a 2, or nothing. Okay? That's different on blackboard too. But a 1, a 2, or nothing. So, for the 1s orbital, sulfur, 1s is full, 2 electrons. 2s is also full, 2 boron. We have 3 p orbitals. 1, 2, 3, 4, 5, 6 electrons. They go in, 2 each. The 3s is full. And in the 3p, we will have 1, 2, 3, 4 electrons. Hund tells us 1 at a time. And then the second electron goes here. And that's the answer. Now, like I keep saying, this is different on blackboards, just slightly, for 2 reasons. First of all, we don't need to do Hund's rule. And secondly, you cannot leave anything blank. As long as I was writing the code, I could do blanks. Blackboard doesn't do blanks. So, you have to do either a 1, a 2, or a 0. So let's do magnesium. Magnesium is here in the 3rd period, 2nd group. That means the first energy level is full, 1s2. Second one is full, 2s2. Here we have 6 electrons into p, 2p6. And here we have 2 electrons in the 3s, 3s2. On blackboard, you would show that with a 2, another 2, a 6. Instead of the 2, 2, 2, you do the total 6. The 3s is also a 2. There's nothing in the 3p, is there? But on blackboard, you must enter the 0. Now again, on an exam, I probably will ask you either to write an electron configuration or to choose one from a list. But it will be in this format, and it'll be simple, okay? First 3 groups, first 3 periods, that's it. All right. Well, if there are no questions, and there always are, I mean, this is, again, the first time you've ever seen quantum mechanics, but I think it's important to understand where the concept of valence electrons come from. Let's move on to chapter 2. We're going to talk about physical and chemical properties. And if you've been looking for Nemo, there he is. All right, back in chapter 1, we said matter. Matter was defined as any substance that occupies space and has mass. If this chunk of matter, the substance you have, only has one type of atom, we said it's called an element. Now, if chemistry only dealt with elements, it would be kind of boring. Turns out that you can take 2 or more elements, combine them together, and make what we will call a compound. A compound is present in a specific and constant pattern. So that means the same numbers and types of atoms in every molecule. For example, this is methane. Methane is natural gas. Every molecule of methane looks just like this. It has one carbon in the middle. It has 4 hydrogens around it. They're all bonded together. The angles here are always 109.5 degrees. Every methane looks just like this. We will see in a bit that there are 2 different types of compounds. This is an example of a covalent compound or molecular. The other is an ionic compound, but we'll do that later. All right, a pure substance. Pure substance contains only one type of matter, okay? It can be an element or whatever. It cannot be easily broken down to other things, but remember, compounds can always be converted back into elements or other compounds, but not easily. If we have 2 or more pure substances, we have what we call a mixture. All right, mixtures come in 2 flavors. One is heterogeneous. That's what we usually think about when we think of mixtures. And the other is homogeneous. These are also referred to as solutions. Heterogeneous mixture. Think of gravel, okay? The difference between heterogeneous and homogeneous comes down to sample. If I reach in this little pile of rocks and I grab a handful from here and a handful from here, they're different. They're obviously different. This is heterogeneous. This picture was taken on a beach, actually in St. John. I took it. It was great. But while I was there, I also scooped up a little beaker full of water. Water is a homogeneous mixture, salt water. It contains water, and the salt is dissolved in it. We know that it's a mixture, however, because if we let this thing just sit there long enough, the water will slowly evaporate, and we are left with the salt. Simple physical means separates the mixture. Again, if we go back to our salt water and sample, if I reach in this side of the beaker and pull out a sample, the composition will be exactly the same as this side of the beaker. Homogeneous. All right, let's look at a couple really simple things here. This is a rock. Is it a pure substance? Well, you look at it and you say it's pure rock. But if we take and we do a thin slice of this and put it under a microscope, this is what we see. This is an aggregate. And again, the sample. If I took this chunk and this chunk, they're totally different, aren't they? And they can be separated by physical means. So it's a heterogeneous mixture. Gold bars. Well, they all look different, don't they? But on a chemical level, atomic level, each of these only consists of gold atoms. It's an element. By definition, it's a pure substance. If you put table salt under a microscope, this is what you see. These are little cubes, kind of cute. They all look different, don't they? But is this a pure substance or not? Once again, on an atomic level, each of these consists of a cubic array of sodium and chlorine atoms. That's all that's there. This is what we call an ionic compound. Again, that's chapter 3. Sodium and chlorine atoms, that's it. All right, let's look at some more. Classify these as pure substance, heterogeneous, homogeneous, or elements. Air, ground pepper, seawater, sugar, gasoline, and gravel. I will pause for a moment. The ancient Greeks told us there were 4 elements: earth, air, fire, and water. They were wrong. Air is not an element. Air is actually a mixture. We know that there's oxygen in here, right? Because we can all breathe. And somewhere somebody told us once that there was nitrogen in there too. And there's carbon dioxide, and there's dozens and dozens of other gases. Yet, if we take a sample from here and a sample from here, they're the same composition. So this is a mixture, and it's homogeneous. Ground pepper. Take your pepper mill, grind yourself a little pile. What do you get? Lots of little gray and black and brown flecks, don't you? If you had the patience, you could sit and separate these into separate piles. This is also a mixture, but it is heterogeneous. We see seawater. Seawater, mixture of sodium chloride and water and other stuff. We can separate it by simple evaporation of the water. It is a homogeneous mixture. Sugar. When we say sugar, it's a very general term. This is table sugar, sucrose it's called. This is the molecular model of it. We will do a molecular model on Wednesday, but called ball and stick because it's little balls and sticks. This is oxygen, the whites are hydrogen, blacks are carbon. This is a compound. Every molecule of sucrose looks just like this, just like that. It is a pure substance. Being a pure substance, it's an A. Gasoline. Well, gasoline is a very complex sort of stuff. Remember or think about the fact when you go to the gas station, you can choose the octane level. Octane is a hydrocarbon, and it burns very well. And the more you have, the hotter, faster it burns. That implies right away that we have a mixture. It is a mixture. Whole bunch of stuff in it. Turns out that aromatics make up most of it. Here's the simple alkanes, the branch alkanes. Octane is somewhere in here. These are other things, but they're all basically hydrocarbons. It is a mixture, and yet if you take a sample from the first and the last drop out of the pump, they're the same. Therefore, it's homogeneous. And finally, our friend gravel. We know gravel, lots of little rocks, heterogeneous. Any questions? All right, let's move on to properties. We're going to talk about physical properties and chemical properties. The simplest of the physical properties is the state of matter. This is an icicle. We will see these before the end of our semester, sadly. And these are melting. As they do that, they're changing from solid water into liquid. This is called a change in state. Physical properties basically include the state, appearance, the density, that is, how heavy something is per unit, melting point, boiling point, refractive index, whatever that is, and other stuff. Physical properties, what something looks like. Chemical properties are going to reflect how things react with other stuff. The most common physical change, you start off with one substance, you wind up with a different substance, but it has different physical properties. The most common physical change is a change in state. That's what we have here. We're starting from a solid, go to a liquid, and finally, if we warm that liquid up, we make a gas. We can look at solids, liquids, and gases like this. These little balls here represent the individual particles in the substance. We have a solid. In a solid, particles are held together. They're held together tightly by what we'll see are called intermolecular forces. If we put energy into the solid, we can start our little particles moving relative to each other, but still not escaping. As a liquid, they just slip and slide all over each other. And finally, in a gas, we have broken all of the forces, and they're just free to go anywhere they want. Transitions. Start with a solid. Solids have defined shapes and volumes. Liquids have defined volumes, but they take on the shape of the container. And gases, free spirit, they take on the shape of anything, and they move very, very rapidly. If we start with a solid, we can go to a liquid simply by putting energy in. The temperature at which this happens is called the melting point. The melting point is unique for every substance. Absolutely unique. That's because the things that hold the particles together, these intermolecular forces we'll see in a minute, are unique for every substance. So the energy it takes to break it is also unique. If we have a liquid, we can heat it up, make a gas. We can actually go straight from a solid to a gas. This is sublimation. This is how frost forms. We have water in the gas phase, goes directly to ice. Doesn't do liquid in between. Let's look at a simple problem. This is bromine. Now bromine is here in the 7th group. It's in the 4th period. It's a liquid at room temperature. This is liquid bromine that has been frozen and then taken out to thaw a little bit. This dark brown stuff on the bottom is liquid bromine. These are the crystals of solid that are still there. And the gaseous bromine is here as this, brownish gas sort of thing. So we have all three phases of bromine here. The melting point of bromine, minus 7.2. The boiling point to go from here to the vapor is about 60. So think about it. If I tell you we have bromine at minus 20, what's the physical state?
It's a green gas.
Well, the melting point is minus 7, isn't it? Minus 20 is less. So it's a solid. If we take it up to 80, the boiling point is about 60. We're above the boiling point. We're talking gas. And minus 0.12. That requires you to think a little bit. You have to go down to minus 7 for this stuff to freeze, don't you? If you're up to 60, it's a gas. We're dealing with a liquid. Now, when you write exams, I'll be honest with you, it's so simple to write an exam that everybody fails. That's no fun. Really isn't. So, depending upon the exact nature of the exam, I sometimes tend to put on questions that I'm pretty sure everybody's going to get right. Makes you feel better, makes me feel good too, okay? So this was one of them, many years ago. Pure substance, 15 degrees above its boiling point is what? A, B, or C? I thought this is so dead simple. Class of 500, half of them missed it. I was taken aback. We talked about it in class after the exam. And I said, you know, for something like this, if you have trouble with the logic, think about a number line. It's really just temperatures, okay? We go from solid to liquid to gas, and the transitions melting and boiling. The problem here says we're 15 degrees above the boiling point. That means we're here. That means we're dealing with a gas. And then everybody understood. So for a while, I put this same sort of question on every exam. There's another version. Melts at 115, boils at 325 at room temperature. What is it? Here's our number line. Here's our melting point. Here's our boiling point. Where is 25 degrees? Way down here. We are solid. One more just to spice it up, I put negative numbers. We melt at minus 45, boil at 4 degrees, and we're sitting at minus 36. Here's our line. This is our melting point. That's our boiling point. We are at minus 36, somewhere in here. It's a liquid. Any questions? Simple concept, just think about it, okay? All right, I have talked several times about this magic intermolecular force thing, right? This is part of what we refer to as a kinetic molecular theory. Kinetic molecular theory says several things. We'll see this again in chapter 9. But it also says that every particle in the universe has an inherent attraction towards every other particle. Now, sometimes this is a strong attraction, sometimes it's weak, but there's always something. Think of buckyballs. Remember these? You can actually buy them again. I can't believe that. These are little tiny round magnets. They're fun. You can make shapes out of them and stuff like that. Problem is that young children thought they were neat too, and they ate them, and that kills you. So don't do that. And don't give them to your kids. But this is an example of a force holding a substance together in a shape. This is magnetic force, but it's the same basic principle. This is a calculation. These are just generic particles. And when I push my little button here, this guy is going to come flying in and hit this. This represents a solid, okay? It's going to transfer energy to the solid. When it does, this will burst apart. The computer actually calculated the trajectories, the everything, the bouncing around, and then slowly, as it hits the container, it loses energy. Let's see what it looks like. There they go. Bouncing around madly, bouncing off each other. As they hit the sides, they lose energy. Getting tired now, slowing down. But the thing to note here is that as they lose this energy, they begin the transition from gas phase. This was probably closer to a liquid phase. They start sticking to each other, don't they? And if we let this sit long enough, the computer will coalesce these into a lump. Intermolecular forces. Kind of neat. All right. Kinetic molecular theory tells us that the thing that determines if we have a solid, liquid, or gas is the inherent energy and the strength of the intermolecular forces. So, this represents a solid. The particles are stuck together. They don't have enough energy to break apart. KMT also tells us that nothing ever sits still like children. Therefore, they just sit and shape. If we put energy into it, we reach the magic point where we have enough energy in that the particles in it can now start moving relative to each other, but they still can't escape. This is the liquid phase. And finally, if we take the liquid and we put more energy into it, we reach the point where we can totally break the intermolecular forces and we get the gas phase.
By energy, we mean heat.
I'm sorry?
By energy, do we mean heat?
Heat, right? Yeah, energy. Heat. Heat is a form of energy. But, okay. So, the KMT tells us about our three states of matter. A gas, the particles are highly separated. Because there's so much space between them, you can compress a gas because of all that space. Attractive forces are minimal, take on the shape and volume of the container. We will donate an entire chapter, chapter 9, to the gas phase. In a liquid, molecules are closely spaced, making it not compressible, takes on the shape and volume of their container. And finally, a solid sits in one spot, basically shakes, defines shape. It is not compressible either. All right, let's go a little more into the concept of other physical properties. Remember, it describes the physical state of a substance, its appearance, or any other inherent property. That's what a physical property is, how you describe something. This is mercury. Mercury is a very fun thing to play with. When I was a child, we played with it all the time. Now it's considered a neurotoxin. So we're not even allowed to have it in the building. Yes. It's a metal. It conducts electricity, and it's a liquid at room temperature. Another physical property that's very important is what's called density. Density is mass per unit volume. Typically, the units of mass we use would be grams. And typically, for a solid anyway, the volume we use is going to be cubic centimeters. For a liquid, we would use milliliters, recalling 1 milliliter is exactly the same as a cubic centimeter. Cubic centimeter simply looks like this. The definition, mass per unit volume. If we have exactly 1 cubic centimeter of gold, that would weigh 19.3 grams. Formula for density, mass divided by volume. Our mass here is 19, our volume is 1 cubic centimeter. Our density is therefore 19.3 grams per cubic centimeter. That's all in the world density is. Any questions? Well, substances have different densities. The density of water is darn near 1. Actually, at 4 degrees centigrade, it is exactly 1. But at room temperature is a little less, 0.996. Mercury, we've seen, it's heavy, fun to play with. Density 13.5 grams per cubic centimeter. So 13.5 times heavier than the same volume of water. Sulfur is about 2-ish. Iron, 7.8. Helium and oxygen, these are gases. Now, these are their densities in grams per cubic centimeter. Okay? These are small numbers. Typically, when you're dealing with a gas, instead of using grams per cubic centimeter, we will do 1,000 cubic centimeters, which is liter. So these are grams per liter. That's just typically done so you don't worry with all these little zeros. You'll also note that helium is much less than oxygen, and that's why balloons float. Now, you're going to see something that's very unusual. This is a gentleman, and he's holding a cannonball. Okay? And he's standing in front of this giant pool of mercury. Now, cannonballs are pretty heavy, aren't they? Pure iron. He's going to take this, drop it in this. I hope he's holding his breath. The surprising thing is, by George, the cannonball floats. Cannonballs don't float on top of many things, do they? Why? Because the density of iron is 7.8. Mercury is 13.5. The less dense object floats. Now, people have a density slightly less than water. So you can actually sit on a big puddle of mercury. Now, this image has a story. It's a sad story, okay? In the early 60s, maybe late 60s somewhere, National Geographic did a story on mercury. And they went to Europe and where they have giant mercury factories, and one of the workers just volunteered to sit on the puddle of mercury. And he floated. They published this picture, okay? They then discovered that this gentleman was severely mentally impaired because of working with mercury for all those years, no protection. So they immediately went and recalled every issue, every copy of this picture they could find. But this is the day of the internet, so they missed at least one. So this is totally unacceptable these days. I feel so sorry for this guy, but that's the way things were back in those days. Problem. We have 250 cubic centimeters of gas, mass of 0.45 grams. What is the density? We recall that this is mass per unit volume. So we want to take our mass divided by our volume. Here's our equation. Our mass is 0.45 grams. Our volume is 250 cubic centimeters. To get the density, all you have to do is a simple division, 0.0018 grams per cubic centimeter. That's simple. We'll actually do this in lab, sort of. Pretend that you were given a rock, and your entire grade in chemistry depended upon determining the density of that rock. Well, okay, no problem. I can weigh it, I get the mass. But the rock is irregular. How in the world do you know its volume? Turns out that this is a very old problem. Back in ancient Greece, there was a guy named Archimedes, like the owl. And there was a king. And the king was given a crown by somebody. It was supposed to be pure gold. The king, however, was suspicious that the goldsmith had taken and mixed lead in with the gold. So he handed the crown to Archimedes and said, figure out if this is pure gold. Well, he thought, gee, I could do that if I could measure its density. It should be 19.3. But in order to get the volume, I've got to melt the thing down. Can't do that. So the story goes, he was pondering this issue and took a bath. As he sat in the tub, water rose up over the edge, down the sides. He screamed out, "Eureka," which is Greek for, "My goodness, I got it." Jumped out of the tub, ran naked in the streets, screaming, "Eureka," okay. What he had figured out was that when you put an object into something like water, it's going to displace the liquid. The amount of liquid it displaces is equal to the volume of the object. So, here is a liquid. We are going to take our rock and add it to this liquid. Before we did that, we measured the level of the liquid to start with. We now measure the level of the liquid when we're done. The difference in these gives us the volume of the water. called the water displacement method. So we started at 22.5, wound up at 45.6. That's how much our rock weighs. What's the density? Simple problem. Mass divided by volume. Our mass is 43. Our volume is the difference in these two. Do our subtraction. We get 23.1 milliliters, which we all know is exactly equal to 23.1 cubic centimeters. Do our division. 1.86 grams per cubic centimeter. Now you will also see this written as 1.86 grams centimeter minus 3. The fact that we have a negative exponent means it's in the denominator. We can also express this in terms of milliliters because a cubic centimeter and a milliliter are the same. Any questions? Another problem. Ethanol. This is the alcohol of consumption. Its density is 0.79. We have 15 mils of it. How much does that weigh? We're going to solve this problem using the algorithm that we introduced for the metric system. That is, given, ratio, and find. Our given here, 15 cubic centimeters of ethanol. Okay? The ratio. For the ratio, we're going to use the density. This is 0.79 grams divided by 1 gram. That's a ratio. Given ratio, we're trying to find grams. Remember, we start off with our given. Our ratio must be set up so the units of given, cubic centimeters, are in the denominator. They are. Cubic centimeters will cancel. 0.79 divided by 15, 11.8 grams. Now that's nice and simple, isn't it? There is one thing. As you look at this problem, remember these are measurements, aren't they? Are the significant figures correct? Well, here we have 4, here we have 3. We've rounded this to 3. That's good. The least significant measurement. But what about the 1? Is that 1 significant figure? No. We refer to that as an exact number. It's not a measurement. It's a definition per 1 cubic centimeter. So yes, this is correct. Round it to 3 significant figures. Density of mercury is 13. We have 999 grams. What's the volume? Set it up using given, ratio, and find. Go ahead and write down your equations. Our given is going to be our 999 grams. Our ratio is our density. We start off with our given. Going to multiply this by our ratio. But wait a minute. This is wrong, isn't it? Grams has to be in our denominator. So what do? Simply flip it over. There you go. Perfectly legal mathematical operation. Now grams will cancel. 999 divided by 13.5. 73.7 cubic centimeters. Let's put density in terms of real life. We have two liquids, we're putting them together. This is oil and this is water. They don't mix, do they? They're going to separate. Which one goes to the top? Well, the density of water is about 1. The density of oil is 0.873. The lowest liquid, lowest density floats on the other, and the oil rises to the top. Whenever you encounter a problem like this, what do you remember? The cannonball. Cannonballs float on mercury. This is a problem that is, kind of like real life lab stuff, okay? We are going to do a reaction. Do our calculation, decide we need exactly 2 grams of acetone. We know its density is written on the bottle. How many cubic centimeters and or milliliters of acetone do you need? Go ahead and set this up with given ratio and find. Our given is our 2 grams. Our ratio is simply our density. We know by now that we need to flip this ratio over. So grams is in our denominator. Start off with our given. Flip this guy upside down. Grams will cancel. 2 divided by 0.79, 2.5 cubic centimeters, which remember in the lab you would measure as a liquid 2.5 milliliters. All right, on your first exam, you will have to do density calculation or 2. Let's look at a couple old problems. Substance with a mass, density of this, what volume is occupied. We kind of just did this a couple times, didn't we? We can do this. If we look at our problem, our mass will be our given, this is our ratio. We can also do it this way. Mass simply divided by our volume is our equation. So we want volume, it's going to be density, it's going to be mass divided by density. Mass divided by density is our volume. Do our simple calculation here on your calculator. Cubic centimeters comes to the top, and you pick your answer. These are the same numbers, but this is liters. Remember, a liter is 1,000 cubic centimeters or 1,000 milliliters. On the exam, you can do it using the equation, or you can do given ratio find. Either one, I don't care, as long as you get an answer, the right one. Here we have a volume of 51 mils, the density of this, what's the mass? Our given here would be our volume. Our ratio is the density with cubic centimeters or mils in the denominator. Simply do our multiplication, pick our answer. We can also do it the longer way. We're looking for mass, substitute, solve for mass, do our division, 74.24. That's what your calculator says. Well, as I look at the answers here, here's 74.24. That's good, right? And here's 74.2. Which one is right?
D.
How many significant figures are in this number? 4 of them. 3 here. 3 significant figures, 3 significant figures, 3 significant figures. Kind of picky, but still not difficult. This is a density conversion problem. We'll see that in just a second. They're not as much fun as the others. We want the density in kilograms per mil. We have 1.5 mils, and here's our mass in milligrams. Oh my goodness. So we're going to have to somehow convert milligrams to grams, grams to kilograms. Our volume is fine. Looking for density, we take our mass, we take our volume, we're going to do our division and get 5687 milligrams per mil. Now, we need to convert this to grams per mil first, because you can do that within your head. How many milligrams in a gram? 1,000. So we're going to divide this by 1,000. That's 5.6 grams. But we want kilograms. How many grams in a kilogram? 1,000. So we divide it by 1,000 again. This is 5.6 grams. Convert that into kilograms by dividing by 1,000. 0.005 kilograms per mil. Simple metric conversion. We've all seen the tutorial button. This is the tutorial for density. I lovingly call this density 1. Everyone likes it. Everyone. You're given a table. One of these guys is missing. All you have to do is type in the missing quantity. We have a mass, we have a volume. Density, we recall, is simply mass divided by volume. We substitute in our mass. Here's our volume. Do our division. 1.37. Volume is missing. Remember, density is mass divided by volume. So volume is mass divided by density. Substitute in our mass, our density. Do the division, 51 and a half. Of course, this next one is going to have the mass missing. Density is mass divided by volume. Therefore, mass is density multiplied by volume. Substitute. Here's our density, here's our volume. Feed it to your calculator, it spits out 54.7. That is density 1. Everybody loves it. On exam 1, it is not unusual for me to go to this tutorial, quick new problem, take the numbers, stick them straight on the exam. Make sure you understand this. If there's a density 1, sadly, there's also a density 2. Density 2 is a word problem, not a table. That freaks everybody out right away. Looking for a volume in cubic centimeters. We have 0.01 kilograms of something. We want our density in grams per mil. Now, mil and cubic centimeter are the same thing. That's no problem. But we're going to have to convert kilograms to grams. Remember, 1,000 grams in a kilogram, so we multiply this by 1,000 to get 15 grams. We're looking for our volume, and we're given the density. We simply take our formula. Oops. Mass divided by our density gives the volume. Type in volume, and we're done. Oh my goodness, it's raining. Oh my goodness. It's raining a lot. Huh. Okay. Another one. Looking for the density in milligrams per mil, we're given this in grams. Also given this in liters. 1,000 mils in a liter, 1,000 milligrams in a gram. Here's our mass in grams. Here's our volume in cubic centimeters or milliliters. Looking for density, simply divide mass by volume. Mass divided by volume is our density, but we want it in milligrams per mil. So we have to multiply this by 1,000. 2213. I really didn't expect it to rain. I didn't bring my umbrella. All right, properties. We've talked about physical properties. Chemical properties basically are going to define how a material combines with something else. Chemical properties, chemical change describes the chemical reaction. When we have a chemical change, we start off with substances that have unique chemical and physical properties. We are going to combine these and form something that is totally different. This is aluminum. This is bromine. Now we've seen bromine. This is liquid bromine in a vial. High vapor pressure. Now you'll understand what that is in general chemistry, actually. That's why we have so much gas above. But nonetheless, here's the reason. What we're going to do is react aluminum, this metal, with bromine, this liquid. Bromine is actually two bromine atoms stuck together. This is bromine in a beaker. This is aluminum foil. We are not doing this on the tabletop. We're doing it in a foot. Take our aluminum, dump it in there. In just a minute or so, as you look at the bottom of the beaker, by gosh, you've got a fire. These fumes that are pouring out the top are incredibly toxic. Incredibly toxic. But when it's all done, you look, and around the edge of our beaker here, by gosh, we have a new substance. This is aluminum bromide. It looks something like this. This is a chemical reaction. We'll talk a lot about chemical reactions in Chapter 5. Basically, a chemical reaction. We're going to show this with an arrow that links reactants and products. The reaction arrow here is an interesting thing. It has the same properties as an equal sign. What that means is that we must have the same numbers and types of atoms on both sides. We also have to have the same mass on both sides, which was a very surprising thing to chemists a long time ago. All right, you can also have physical changes as well as chemical changes. In a physical change, the test of it is we start off with one substance, wind up with the same substance. It's still water. Solid versus liquid, but it's water. We can take water, though, we can run electricity through it. When we do that, we wind up with oxygen gas and hydrogen gas in the ratio of 2 to 1, actually. Water is H2O. This is a chemical change. Our substances have totally different properties than the water we start with. All right, as I said, chemical equation, reactants going to products. Same numbers and types of things on both sides. An example, here we have potassium metal, that's a K, right? Reacting with water, H2O. We are going to form potassium hydroxide and hydrogen gas, H2. If you look at the numbers and types of atoms, we have 2 potassiums. The little s means it's a solid. We have 2 molecules of water, H2O. The 2 here means 2 hydrogens for every oxygen. This 2 means we have 2 waters. We wind up with 2 potassium hydroxides. AQ means it's dissolved in water, aqueous. L is liquid. H2 is a gas. 2 potassiums, 2 potassiums. 4 hydrogens, 1, 2, 3, 4 hydrogens, 2 oxygens. Same numbers and types. In chapter 5, we will do this exercise. It's called balancing an equation. Lots of fun. This is a fun reaction too, because this gets so hot as it reacts that the hydrogen gas that's formed reacts with oxygen in the air and it burns. Kind of a neat thing to do. This is water. This is our potassium solid. It's under mineral oil, just an oil to keep the air away from it because it would react with air too. We'll take a little piece out and we will start our reaction. As it hits, instantly it melts, bounces around the surface, and it's gone. You'll note the flame. That was the hydrogen reacting with oxygen to form water. This is a really fun reaction. You have to be careful. If you put in too large a chunk, it will get so hot it'll explode on you. Again, not something we can do on the tabletop, but it's a fun thing to do. The hydrogen reacting with oxygen, that's also fun. It's a little movie clip. This is a burner on a long stick. Brave guy out here somewhere. This is a balloon filled with hydrogen gas. This is a room filled with oxygen. Very carefully. Really fun thing to do. All right. Are these chemical or physical changes? If we take a gold bar and hammer it into gold leaf, metals have a physical property called malleability. Gold is the most malleable of all the elements. You could actually take gold and pound it so it's just several atoms thick. It's amazing, and it still looks just like gold. When you see a cathedral that's covered with gold, that's gold leaf. Probably a gram of gold in the whole thing. You just pound it out really, really thin. But you start off with gold, you wind up with gold. It's just thin. Physical change. If we take water and we heat it up till it boils, what's that? It's still water, isn't it? Started out water, ends up water. It's just in the gas phase. And finally, if we burn a bar of carbon, we get carbon dioxide. These two totally different substances. This is a chemical change. Now we talked a little bit about same numbers and types of atoms on both sides of an equation, right? I also said that the mass was the same on both sides. This is something that was not clear to early chemists. It's called the conservation of mass. Lavoisier was a French chemist. He messed around using this apparatus with mercury and mercury oxide and was the very first one to demonstrate the conservation of mass. What he did, he started with mercury, heat it up, and you make mercury oxide. He very carefully weighed how much mercury, how much oxygen was consumed, and the mass of this stuff. Then he took this stuff, heated it up, and went back to form mercury. He weighed the mercury, weighed the oxygen that was given off. The equations look like this. Mercury plus oxygen, mercury 2 oxide, mercury 2 oxide plus heat, mercury and oxygen. The conclusion was these were exactly the same. At the time, nobody suspected that at all. This was a totally novel observation. The guy was really smart. Problem was, he looked like this. That's his lovely wife standing next to him. The other problem is, this was the time of the French Revolution. And the French peasants hated people that looked like this, even though he was brilliant. He was immediately arrested, thrown in jail. The chemists of the world objected. They petitioned the court, let this guy out. He's really smart. He's good. The French court issued a ruling, and they said, the Republic, that's France, needs neither scientists nor chemists. And they sent him to the guillotine, and that was it. It's a shame. Really smart guy. Maybe that's what's wrong with France today. Who knows? Okay, a couple more questions. Which of the following are a physical change? Lighting a match. Well, when you light a match, it goes from this little match head to a burned match head. And there's smoke that comes off and everything like that. That's not physical, that's chemical. Sugar and tea. Well, when you're done, what do you have? Sugar and tea. Homogeneous mixture. It's a mixture. Melting of aspirin. Yes, aspirin really is a chemical compound, and you can melt it. But it's still aspirin. Just change state. B and C are both correct. Which are chemical properties of carbon? It's a solid. It's insoluble in water. Surprisingly, it is soluble in carbon tetrachloride. Reacts with oxygen, and it crystallizes to form diamonds. Well, the diamond is still carbon, just a different physical state. Reacts with oxygen, that's a chemical reaction. It's soluble, it's not soluble, these are all physical. D is the correct answer. Compounds cannot be decomposed into elements. Well, yeah, they can. Both elements and compounds are pure substances. Yeah, they can. They are. Elements but not compounds are pure. This is the only correct one. Compounds, of course, can be decomposed. We have three elements that are unknown. One is cadmium, copper, and zinc. Densities of 8.6, 8.9, and 7.1. We have a metal with a volume of 15 and a mass of 133. Which one is it? What you have to do here is simply take our mass, divide it by our volume. and determine our density. Turns out to be 8.9. We're dealing with copper. All right, on Wednesday, we will do our first lab. Please remember to bring your safety goggles. It's a very simple lab. You must print the handout that's on Blackboard. Okay, print that, bring it, because you have to hand in the last page as you leave the lab. Today, we covered atomic configuration, electron configuration, density 1 and density 2. This gives us 1, 2, 3, 4, 5, 6, 7, 8 tutorials. That's 40 points worth. Oh my goodness. All right, enjoy the rainstorm.